Key schedule security for the TLS 1.3 handshake. Let us start with the TLS handshake. The TLS 1.3 handshake protocol is a key exchange protocol which allows the client and the server to agree on a symmetric key K, which they can then use to build a secure channel to authenticate and encrypt their communication. And I will now focus on the handshake protocol, so let me remove the secure channel. At the core of the TLS 1.3 handshake protocol is a one-sided authenticated Diffie-Hellman protocol, so the client sends G to the X, the server sends G to the Y, and then additionally the server sends a signature over G to the X and G to the Y, and then both parties authenticate the transcript with a MAC. Additionally, the client and the server might have a pre-shared key, and if so, then the client sends over the ID of this pre-shared key and a binder value that binds the pre-shared key to the transcript. And then the resulting session key should be secure if the PSK was honest or the Diffie-Hellman secret was honest. So how does this work? We first feed the PSK into some deterministic function indicated by this pink arrow, and then we run an extract function to get a new key value on which we apply this deterministic blue function, and then additionally, using a label and a transcript, we derive the session key. Now, the pre-shared key can either come from some external application, or it can be a resumption key which was derived in a private session. So in addition to the session key, we also derive a resumption key. And in fact, we derive many other keys, but I'll skip these in this overview. So in our security analysis of the TLS 1.3 key schedule, we model the key schedule, so we model key derivations, not the protocol flow, and the adversary chooses its own corrupted keys and Diffie-Hellman shares, and it can instruct the model to sample honest keys. So this model is a strong version of selective corruption. And additionally, the adversary instructs the model to perform key derivations with adversarially chosen transcripts that have to satisfy some restrictions. And in this model, we prove that the session keys are pseudo-random and unique. Pseudo-randomness holds if the last PSK or Diffie-Hellman secret were honest, and uniqueness also holds for all dishonest keys, which follows from the restrictions on the transcript. In our security analysis, we assume that the expand function is a pseudo-random function, that the extract function is a dual pseudo-random function, and additionally we assume collision resistant on the expand function, the extract function, and the hash function involved in the protocol. And additionally, what our analysis brought to light was the need for the salted oracle Diffie-Hellman assumption, which is an assumption where the adversary can choose the salt, because here in this protocol, this pink function is a deterministic function of the pre-shared key. So if the pre-shared key is dishonest, then the adversary has a lot of control over the salt that is used in this extraction step here. For the PRF assumptions and the collision resistance, we did not need to make agile assumptions that talk about relations between different algorithms, but for the salted oracle Diffie-Hellmans, we did need to make an agile assumption, because potentially from the same Diffie-Hellman secret, one might extract with pre-shared keys that use different algorithms. I would like to conclude my presentation with a couple of afterthoughts on protocol modifications, which would have made the analysis considerably easier and would have allowed us to rely on a weaker oracle Diffie-Hellman assumption. Firstly, it's very nice for the analysis to include the context early. Here, by context, I refer particularly to the resumption level and the Diffie-Hellman shares. Secondly, it would be a good idea to extract from the Diffie-Hellman secret first before mixing it with other secrets. Including the resumption level explicitly early on in the PSK derivation prevents collision attacks between resumption PSKs and external PSKs more directly than currently done in TLS. Similarly, extracting from Diffie-Hellman first and then including the Diffie-Hellman shares into the derivation allows to prevent collision attacks for this kind of Diffie-Hellman key. Additionally, it would allow the analysis to rely on a less strong Diffie-Hellman assumption.